Deep knowledge about the e-mobility sector and information about how to charge your electric vehicle with the power of the sun. This is, of course, the topic in our today's webinar here at the Fronius e-mobility expert training. I welcome you here at Fronius today. My name is Michael Raunig, and together with my colleague Hans Pelzer, we will guide you through this webinar today. If you have any questions during or after the webinar, please feel free to ask us these questions in our live chat. So you can always use our live chat function here in the webinar to ask us your questions, and we will then answer it to you. Hans and me, we are part of the team trainings and educations here at Fronius International in the business unit Solar Energy, and we are here for you to keep you up to date and give you topics and good information about the new topics here at Fronius. So let's have a look first on what's on the agenda today. First of all, we will give you basic information about the e-mobility sector. So which charging standards are out there, which factors of charging power are reliable for charging your electric vehicle at home or at public charging stations. Second up are then the e-mobility provider. So we'll have a look on what is the e-mobility provider, what does he do, and what about public charging and public charging stations. Furthermore, we will talk about the topic of e-mobility and photovoltaic. So we will have a look on the energy usage that is needed for charging your electric vehicle on the PV side, and furthermore, charging your electric vehicle with the power of a PV system. Last but not least, we will talk about the charging solutions. So we will give you an overview about the Fronius charging solutions, what is possible today, what is the Fronius energy management, what is a step charging process, and how can a car be stepless, so dynamically controlled with charging. Last but not least, we will talk about the economic potential of the solutions, so you will get to know what's on the money side of these charging solutions. So first up, let's start with the e-mobility basics. Let's talk about batteries. Of course, the battery is the heart of every electric car out there. And if we now compare it to our stationary storage systems, so in photovoltaics, we are always talking about small stationary storage to store the electricity, the PV surplus energy that comes from the roof and cannot be used in the house. So therefore, we are talking about stationary small storage systems. And of course, what fits in such a stationary storage system is from about 5 kilowatt hours of usable capacity up to 20 kilowatt hours of usable capacity. So depending on the PV storage that you are buying for your system, it can store about 5 to up to 20 kilowatt hours of energy. So this is the energy content that we are talking when it goes about PV systems. Second up, of course, regarding electric car batteries, they store a lot of more of energy. So when we talk about modern electric cars, they store from about 40 kilowatt hours of capacity up to, for the big cars, up to 100 kilowatt hours of usable capacity. So as you see, this is the first of a correliance here that we are talking about relatively small stationary storages with a smaller usable capacity. And then we have the big car batteries, and they are a very big storage in comparison to these small stationary storages. So first hint here, if you have a nighttime charge, so if you want to charge your car in the nighttime, please make sure your full car battery can't be charged from such a small stationary storage. What can be done, although, is that you charge up a percentage of your car battery. So let's take into account, for example, when you have a commute of about 60 kilometers per day, you can easily charge up the 60 kilometers of range that you need from your small stationary storage. So as you see, depending on the usage that you want to use your electric car, it is very different from charging up the full car to charging up part cycles of the car. So only small circles of the car itself. So for example, charge it from 50% up to 80% of capacity. Charging the car, of course, nothing happens without charging, and therefore regarding charging, we are having two forms of charging. First of all, we have the AC charging, so the alternating current charging. And of course, this topic regards often to home charging. So if you charge your car in the own garage or in the carport, or of course, if you charge it in a public place like a supermarket, or for example, at a hotel. So for this AC charging, for this alternating current charge, it is always necessary to have an AC wall box or an AC charging station on the infrastructure side. Therefore, we need a so-called onboard charger. And this onboard charger, this is inverter. So this is an AC-DC inverter that is built into the car. So as you see, when it comes to AC charging, it is always good to know that you know which inverter, which onboard charger is built in the electric vehicle. So there are different forms of these onboard chargers, and they determine with what power you can charge your electric vehicle. So on one hand side, the infrastructure for AC charging, of course, is relatively cheap because all you need is AC power. And of course, AC power is there everywhere. And then you need just a charging socket, for example, or a charging station to plug in your electric vehicle on AC side. So this AC DC converter, this onboard charger, is very important when it comes to AC charging. However, this charging process can, of course, take up to several hours because the wattage, so the power that can be delivered to the car, is limited either to the housing connection or, of course, to the charging station itself. So therefore, we are talking about the residential charging with this AC, with this alternating current charge. On the other hand side, we have the possibility of fast charging with DC power, so with direct current. And as you see it in the picture on the right-hand side, this DC charger, this is then on the infrastructure side. Here, the AC-DC converter, so this inverter is built in the infrastructure side. So therefore, it is possible to plug in your electric car via a DC cable. And therefore, of course, the power can be much higher because you don't have to use this AC-DC converter in the car. So no need of an onboard charger. You are just charging directly with DC current via a bypass, and you are charging your electric volt battery directly. So in this case, you have significantly shorter charging times because you can charge with higher power. And nevertheless, the charging infrastructure, so these DC fast chargers, are much more expensive than the AC chargers are. So therefore, you have to pay for the infrastructure if you want to charge with DC fast charge. So these are the two different charging types. And furthermore, there are two different charging standards that are used today for charging up an electric vehicle. On the one hand side, we have on the AC side for the alternate current charge, we have in Europe the so-called Type 2 plug. And this Type 2 plug that you can see on the picture on the left-hand side, this was called as a standard for all European nations. So the Type 2 plug is more or less a power socket. So in this case, we have a three-phase power socket. And here with the Type 2 plug, we have a three-phase charge plug that you can charge your car with. So first of all, of course, this Type 2 plug consists of three phases, a neutral contact and a protective earth contact. Furthermore, we have the so-called CP, this is the control pilot, and we have the PP, the so-called proximity pilot. And in this case, the CP is there for communicating from the car to the charging station. So for several reasons, like for example, safety reasons, we have this communication contact, this control pilot, that the car can communicate with the charging infrastructure. And therefore, the car, for example, can tell the charging infrastructure the current state of operation that the car is in. So for example, the car can start the charge and end the charge via this CP contact. On the other hand side, the proximity pilot is there with a resistance, and this contact tells the charging infrastructure which maximum current can be used on this charging cable. So these type 2 charging cables, they are coded and they have different charging currents available. So for example, there is a 16 amp charging cable, and there is also, for example, a 32 amp charging cable. So depending on which charging cable you are using, you can achieve different charging powers in the process. So typical charging powers with the type 2 plug are, for example, 2.3 kilowatts of power. They can even charge with 11 kilowatts of power, for example, 3-phase, and even with 22 kilowatts of power, 3-phase. The type 2 plug, however, is made up to 43 kilowatt of charging power. So you see it's a relatively important standard that we have here. And it just makes sure that you are always compatible with the car, with the charging infrastructure. On the other hand side, with the direct current standards, we have in Europe two main current standards at the moment. First of all, there is the so-called CCS plug. So this is the combined charging system plug. And as you see, it builds on the topology of the type 2 plug. So besides the communication ports, the control pilot and proximity pilot, we have extra to that on the lower side of the plug, we have a DC plus and DC minus connection. And these connections are used for delivering the direct current DC to the electric vehicle. So as you see, you can use this in one plug, and therefore the CCS plug is a very common standard in Europe and is often used, for example, on the motorways, on the highways, and of course, everywhere where you want to charge up your car really fast. Second one is then the CHAdeMO plug. And this CHAdeMO plug is often used by Asian manufacturers, like for example, Nissan. And this is also a fast charging topology, and it also has two DC plus and DC minus contacts to charge up the vehicle with the DC side. Typical charging powers for DC fast charging are around 20 up to 350 kilowatts. So you see these fast charging standards, they are probably of having a very high charging current, so you can charge with a very high power. Furthermore, typical charging powers are around 50 kilowatts, for example, or 150 kilowatts of power. So let's have a look on range and mileage of car. So for our calculation, we now take an example. So for example, the range of an example car like the Hyundai Kona is, we are always talking about kilowatt hours that the car is using. So for example, the Hyundai Kona uses about 15 kilowatt hours of energy for 100 kilometers of range. So if we now assume that we have an energy price of around 20 cents per kilowatt hour, this gives us around 3 euros to drive 100 kilometers of range. So if we now assume that this Hyundai Kona has a battery pack of 64 kilowatt hours of usable energy, therefore we can drive with it over 420 kilometers of range. What's now very important to note when we are charging this battery on the AC side, so if we make an AC charging with it, we always have to point out the fact that there is an efficiency for AC charging. So this onboard charger on the car, it has a given efficiency, and most of the chargers are around 90% of efficiency. So we have 10% energy losses during the charging process. So if you now want, for example, make sure that your car has 100 kilometers of range at the next day, and you want to charge therefore 15 kilowatt hours of power, you need to put in 70 kilowatt hours of power into the car to make sure that you get these 15 kilowatt hours of power in the car battery to drive this 100 kilometers of range. So please make sure you always have to take in mind this required energy for AC charging. Okay, furthermore, there are limiting factors for the charging power. So if you now want to charge your electric vehicle, you have to keep these 4 different factors in mind. First of all, the first limiting factor can be the supply line or the fuse protection of the household. Let's assume you are charging your electric vehicle at home And therefore, you need to make sure, first of all, that you have the correct supply line to the charging station, and you have a correct fuse protection for making sure that the fuses are not triggering if you're taking too much amperage from the charging station. So this supply line and fuse protection can be one limiting factor of the charging process. Second up, of course, is the charging station or the mobile charging cable that you are using. So every charging station has a given amperage, a given power that you can charge with, and therefore you need to make sure to choose the right charging station or the right mobile charging cable to charge up your electric vehicle at the given amperage, at the given power. Third up is then, of course, the type 2 charging cable. So depending on what is the given amperage of the charging cable, this limits your charging factor. So for example, if you're charging with a single phase charging cable, this of course depends on your charging power that you can use during the process. So please make sure that you're choosing the right type 2 cable for charging the electric vehicle depending on your needs. Fourth different factor is then the onboard charger in the vehicle. And depending on this onboard charger that is built in the electric vehicle, this is again one of the 4 different factors that conclude your charging power. So there are lots of different onboard chargers built in the cars nowadays. So for example, there are manufacturers, they are building in only single phase onboard chargers. And there are other manufacturers, they are building in 3-phase onboard chargers, for example. And of course, it is always very good to know which onboard charger your electric vehicle has, because all these factors, they conclude in your total charging power that you can achieve. So of course, always the weakest link in this chain, so the weakest component of these 4 components, they are decisive for the charging performance that you can actually achieve with. So for example, if you have a very strong house connection, very strong supply line, and a very strong charging station, and then you are plugging in the right type 2 cable, but you only have a single phase 3 kilowatt onboard charger, for example, then you can always charge with the limiting factor of the weakest component in this chain. So please make sure there are 4 different factors that differ on your charging process. Okay, so now how can charging take place in the home site, so in the household, for example? First of all, there are 2 very basic variants. You are just installing an energy socket, so electricity socket, to the garage or to the carport of the customer. So you can do this, for example, single phase with this blue CEE Cara socket, for example, and of course you can also do it 3-phase with a red power socket. In this case, you always need a so-called ICCP cable. So this ICCP cable, it is an in-cable control box cable. With this cable, the communication is done between the car and the charging station, so the socket in this case. And this is a very easy installation, of course, because all you need to do is to install the socket in the garage and then use such a cable, such a mobile connector, to charge up the electric vehicle. In the best case, you can then control this charging socket to control the charging process itself with a PV surplus energy, for example. So this is a very basic way of charging up the car. The second possibility is then charging with a wall box. So in this case, with a charging station. And there you have the possibility of a fixed installation. So this is no longer a mobile solution then, but it is a fixed installation, and you're installing this charging solution in the garage, for example, and then the customer can plug in with a type 2 plug, or there are also fixed type 2 cables to some charging stations. And therefore you can make sure that the customer has a very high comfort in his garage. He just needs to plug in his car and is all set to go. Depending the powers of the different charging solutions, they can differ. So for example, from 6 amps at the single phase up to 32 amps 3-phase. So you can charge from 1.4 kilowatts up to 22 kilowatts. This, however, always depends on the situation at the household. So depending on the fuses and depending on the house connection, you always need to make sure that you don't exceed the maximum amperage of the household, of course. So why should you now use such a solution with a mobile cable or with an electric vehicle charging station? Most of the suppliers, most of the electric vehicle suppliers, they are delivering such a Schuko cable, so a standard power supply cable. And of course, you can charge up your electric vehicle with this standard charging cable. And for example, plug in a Schuko socket and just plug in at the normal wall plug to charge up your electric vehicle. The problem is that these charging solutions from the manufacturers, they are often limited to only 10 amps of power. So in this case, for an electric vehicle, this would mean we have a very low charging rate, and therefore charging can take several hours, and this of course takes a lot of time. On the other hand side, the normal Schuko plugs, so these normal sockets, they are not made and not suitable for high continuous current. So they don't like it when you put too much current on it and make it to a too high power output of the socket. And therefore, we recommend to either use such a plug like you saw in the last picture, or to just use an electric vehicle charging station, of course. Next up are now the e-mobility provider. So this is now about public charging and how public charging can take place in the first place. So we have now an example. The customer comes with his electric car to a charging station. So this is a public charging station, for example, at the supermarket or at the hotel. And therefore, of course, the charge point operator, in this case, the hotel or the supermarket, they want to charge or build a process of charging to the customer. So now we have two different possibilities of paying for this charging process. First of all is, of course, charging with a contract. So in this case, the end customer has a contract with a so-called e-mobility service provider. And this e-mobility service provider gives the customer, for example, such an RFID card. And with this RFID card, the customer can go to the charging station and register himself and therefore build the charging process to his account. Furthermore, there's the possibility of a smartphone app. So for example, the e-mobility service provider is delivering a smartphone app to the customer, and then he can register with the smartphone app at the charging station and can charge his electric car on his bill. Second possibility is then the direct payment. So the direct payment gives you the opportunity to bill your charging process with a credit card or, for example, with PayPal. So in this case, you are just opening up the web browser of the charging facility provider, so the charge point operator, and then you can just log into his interface and charge or build the process with PayPal or the credit card. So this is called the ad hoc laden, ad hoc charging. And in this case, we have the direct payment via a credit card, for example. Of course, if you have a contract with an e-mobility service provider, this will come at a cheaper rate. So depending if you are doing a direct payment or charging with a contract, you will have a cheaper charging solution with charging with a contract. Instead of a direct payment, this will come at a higher rate for charging. So how does this charging contract now works with the billing process? So first of all, let's assume the customer comes with his car to a charging station and he connects to the charging station. Then he is authentication himself with an RFID card at the charging station. And therefore, the charge point operator, the so-called CPO, this can be, for example, a hotel owner or a supermarket. He is then billing this charging process to a so-called EMSP. This is the e-mobility service provider. And this e-mobility service provider does the so-called back-end process. So this back-end process is then vital for billing the charging process to the end customer. So for example, there are lots of different charge point operators like Ionity, Fastnet, and Allego, and they are delivering the charging stations, so the charging infrastructure, and the charging process, so the billing process itself. This data is then sent via the backend process using the so-called OCPP. This is the Open Charge Point Protocol. And with this OCPP, it is possible to forward the data of the customer. So for example, the name of the customer, the ID of the customer, and of course, the charging process and the charging time to his account. And then with this information, the e-mobility service provider can forward the invoice to the end customer, to the car user. So the e-mobility service provider in this case has a contract with the end customer, and the end customer gets an invoice from his e-mobility service provider to pay for the charging process he has done on the charging station itself. So you can somehow compare this process of the backend billing like we have with a smartphone provider, for example, with a tariff provider. So the end customer, all he needs to do is to set up a contract with an e-mobility service provider, and then he can use his card, for example, his RFID card or the smartphone app to pay at the charging station. So this is, of course, a very important process because it makes sure that the end customer can charge different charging stations while he is on his travel. Regarding public charging, of course, there are some points to point out. And for example, often shopping centers and hotels, they offer some free charging for now. So this is, of course, a very good way to charge up your electric vehicle for free while shopping or being at the hotel. And then, of course, it is always good to get a charging app or a charging card because, as I told, the charging costs, they can differ if you have a direct payment or if you have a contract. So most of the time, it will come cheaper if you charge with such a contract instead of having a direct payment. Third possible step is then, of course, the charging power. So depending on the charging power that you are using, the costs also differ. So the higher the charging power is, the faster your electric vehicle is charging. But of course, this process also is more expensive than charging with a low rate of power. So therefore, for the end customer, there are lots of different apps like Wattfinder, for example, and he can use these smartphone apps to find the nearest charging station in his area. Okay, so now let's have a look on the e-mobility and photovoltaics. So how to compare photovoltaic with the e-mobility sector. First of all, we have an example for a normal four-person household. And in this case, for example, this household is using about 4,000 kilowatt hours per year of electric energy. The household furthermore has an electric car with 15,000 kilometers per year. So this is the driven distance per year. And therefore they have a consumption per day of 7 kilowatt hours of electricity or per day. So in this case, when you're building up an electric vehicle, we have an additional energy demand for the electric vehicle. So for example, for this electric vehicle with these 15,000 kilometers, we have an additional energy demand of 2,600 kilowatt hours per year. So in this case, please make sure when the customer has an electric vehicle or wants to buy an electric vehicle, you need to make sure that you calculate this surplus energy, the more energy you need, into this calculation. So for example, like we have a typical PV sized system for this 4,000 kilowatt hours of electric energy that is needed, the customer would probably buy a PV system of about 4 kilowatt peaks. So in this case, with this 4 kilowatt peaks, this will be sufficient to cover these 4,000 kilowatt hours of electricity. But in the case he's buying an electric car and has an additional energy usage of 2,600 kilowatt hours, we need to make sure to cover this additional power with the photovoltaic system. And in this case, it is necessary to have an additional PV for the EV itself. And this will be around 3 kilowatt peak of power. So in this case, you are not installing a 4 kilowatt peak system on the roof, but if possible, you are installing a 7 kilowatt peak system on the roof to cover up this additional energy that is needed for the electric vehicle. When it comes about the storage, of course, the normal storage capacity for such a household would be around 5 kilowatt hours of energy. And this will be enough to cover the household loads in the nighttime, for example. But if the customer now wants to charge up his electric vehicle during the nighttime, for example, he is not at home during the day and cannot use the PV surplus energy, we need additional energy for charging up the electric vehicle in the evening hours. So in this case, we will build a bigger battery system. So instead of 5 kilowatt hours of usable capacity, we will have to build up 10 kilowatt hours of usable capacity for this system to cover up one of the side, the load of the household, and on the other hand side, the electric vehicle consumption, of course. So please make sure when you're building up a PV system with an electric vehicle, make sure that you have it covered up, that you have the energies covered up, and of course that you take in mind that an electric vehicle uses energy during the year, and therefore you need to make sure that enough PV space is available for powering up the electric vehicle and supplying the electric vehicle with energy. One point about fact and figures about the range, and therefore most of the customers, they are afraid of long charging times. Nevertheless, if the customer can charge up his car every day, for example, if he comes home, has a commute, the charging times is not necessarily be long. So for example, we have an assumption with 17 kilowatt hours of 100 kilometer consumption. And for example, the customer can charge his car with 3.7 kilowatt of power. So this would mean that he can recharge a range of 20 kilometer per hour of charging. So in this case, if he charge with the current rate of only 3.7 kilowatt, when he charges his car for 3 hours of time, so he charges every day, three hours after work, then he gets about 60 kilometers per day. So in this case, if you assume he has a commute to his work and back of 60 kilometers, he can recharge these 60 kilometers in only 3 hours of time. And I think this is a very good charging rate, because if you come home after work, for example, at 5 o'clock or 6 o'clock in the evening, and you can maybe use 1 hour of PV surplus energy at least, then you can charge 2 hours further, and then you have again your daily commute charged in the electric vehicle again. So this is a very straightforward process, but of course it needs to make sure that the customer is plugging in his electric vehicle every time he has the possibility to. Okay, so now let's have a look on single phase and three phase charging. So basically on a three phase charger, of course, there is a higher power possible. So in this case, if you charge your electric vehicle with a three phase charger, you can, for example, charge with up to 11 kilowatts of power at home. On the other hand side, if you only charge a single phase system, for example, your car can only charge single phase, or your household connection is only single phase, you can charge with a maximum of 3.7 kilowatts. And of course, this is for most of the customers a problem, because they want to have faster charging. So they would have long charging times. And there is now a solution for charging faster on a single phase. So therefore you can just charge up with the PV system. So let's assume that your household connection is about 16 amps. So you're limited to the 16 amps from the grid. And then you can just add up 2 kilowatts coming from the inverter. So in this case, with our energy management, you can make sure that you're using this plus 2 kilowatts for charging up your electric vehicle. And therefore, you can charge with a rate of 5.7 kilowatts of power without maximizing the household connection. So in this case, you can charge up on a single phase with 5.7 kilowatts and not stressing the house connection itself. So your fuses will not trigger, because the 5.7 kilowatts are only delivered when the inverter is producing this 2 kilowatts of power. So therefore, with this situation, you can charge up to 50% quicker than normal charging on a single phase. Next up are the charging solutions, and we will have a look on how Fronius has different charging solutions to offer for you. And therefore, I want to ask my colleague Hans to do the Fronius charging solutions with you.
Yes. Hello. Welcome. I'm very pleased to introduce you the Fronius e-mobility solutions now. Basically, why do we need that, or why do we need communication between the inverter and the wall box or the EV charger? As you can see on the left-hand side, if we have no communication, and the customer would arrive probably at 4 p.m., let's say, and charge his car with 11 kilowatt for a very short moment, actually, because that's maybe the driving distance what he did this day. Then you see that most of the power is coming from the grid, and only 1.8 kilowatt is coming from the PV, from his own PV installation. Therefore, you see, this is really the worst case scenario. What we have, basically, it's bad for the grid because of this peak load for a moment, which you imagine there are many cars doing that. This will cause some troubles. And on the other hand, of course, you're not using your PV power. Therefore, it's much better to do it with the control of the battery from the inverter. If we use our digital IOs, what we offer standard on all our inverters, you start the charging process with a lower power and use, in this example, only maybe 4 kilowatt for the charging. And as long as you have PV power available at a certain amount, and then we additionally charge at nighttime to charge up the car to 100% SOC value in this case. So in this, we use much more of our PV power, about 6 kilowatt hours. And secondly, we use probably on cheap night tariffs, what we also have in many countries. The third possibility is the dynamic PV power control. So we use only the surplus energy and to charge the EV exactly with this power. This is what we see in the green graph here below. That the charging energy is following the PV power. So we have a very high self-consumption of 9 kilowatt hours on that day, and we don't need night charging probably as well, because the car is already fully charged at the later afternoon. So these are the three possibilities, and of course I would like to focus on the second and third solution, because this is what we are offering with our inverters. And how does it look like? If you open the Fronius inverters, snap inverters front panel, you see the orange plug in the middle. This is the data manager card as well. And here you have an output, a digital output, 4 digital outputs actually, with 12 volt signals with 3 watt, which you can use to control a relay, and the relay then will start the charging process in the EV charger. Second, so the pins are below the pins 0, 1, 2, and 3. These are the 12 volt outputs. And then you use the ground, these 2 pins, to connect the 12 volt relay. Or the other way around is the Ethernet plug, Ethernet interface. Here we have our Modbus TCP or Solar API protocol, which is an open interface for other third-party devices. In this case, our EV charger, if they can read out this protocol, of course. So these are the interfaces, the plugs. Whenever you use the digital IOs, you just connect your mobile phone to the inverter, opening the access point, connecting each other, and then you go to load management. And the load management, you will find the first output, load management 1, and you start that, for example, with PV surplus energy, so the activation. First. Second, you set the threshold at what value we would like to switch on. This example, I just set a feed-in power of 2 kilowatt. So when I have a charging power of about 2 kilowatt, let's say, and I switch off at a small consumption. You know, when you have a small consumption, it doesn't matter if it's only low consumption. You could also set it, of course, to feed in at a certain value. But you must make sure that the power, the charging power, is within this range. Yeah. Then you set the duration. What we recommend is a certain minimum duration of 10-15 minutes. You know, we would not like to switch on and off all time. So basically leave it with these 10-15 minutes around. And you can set desired duration as well. So that means this is our night charging. Whenever we set here a certain time, let's say 6 o'clock in the morning when I would like to leave the house, and then I set in 360 minutes. So that means from 12 to 6 a.m. we get here this additional charging whenever we had a cloudy day on the last day, and so there was no charging in the later afternoon. So basically that's all you need to do, and then you just confirm that, and the settings are done. The other way is with the Modbus signal, Modbus protocol. We can also set this here on the Modbus. You can set it to Modbus TCP, or standard is Solar API setting, and that means that we, depending on the third-party device, whatever they can read out, you just select here the data export via Modbus. Now to the solutions. First, load management. Basic, easiest solution with just plug in the garage socket of, let's say here in this case, a caravan socket, 230 volts, single phase. This is recommended, don't use the standard socket. And then the relay, 12 volt relay with a coil power of maximum 3 watt. And then we just switch on the socket. We just switch on phase 1 to the socket. And on the socket, you plug in your ICCP cable. The inverter is connected to a smart meter. A smart meter is always recommended as well on the feeding point, because we want to know what surplus energy is available. If you don't have a smart meter, you can also do it, but then it's only with the PV power production. That means whenever we have production, you start, but you never know what other consumption you have in the house. So therefore, it's recommended to use the Fronius smart meter as well. Or you can also start here an EV charger, a wall box, like for example here Keba. They have an enable input. Also Manic is offering that. So that means you can just give a signal from the relay, a potential free contact, to start the charging process. Yeah, so that's also possible to do. And of course you can do it single phase or 3-phase, whatever you like. That's easy installation, low cost, and it's a very effective solution. You use your PV power and you use also your night charging process. So that's a quite simple, easy process. Yeah. Now, how does it look like in SolarWeb? In the daily production curve, you can see that we connect our car at 4 p.m. Then it's charging with about 3 kilowatt. This is the adjusted charging power, and then whenever we have a certain threshold where we come below with the PV power, then it's switching off. And additionally, at nighttime, let's say in this case 1 a.m., it's charging again for another 2 hours, about 2 hours to completely charge the EV. So that's the kind of security charging to make sure that the customer has his car charged in the morning. So that's the one solution. The second solution is the dynamic control. So we really now using our surplus energy, and we're charging according to the surplus energy of the PV system. So that's a stepless control. That's be done here in this case with the eCharge CPH1 from a German manufacturer. And what you need here is an Ethernet cable, a LAN cable from the router to the wallbox. And the inverter is just connected to a smart meter, a feeding point, and then connected to the network, to the router as well. So we are Wi-Fi or LAN as well. And here we read out the data and we send data to the wallbox, and the wallbox is then charging according to surplus energy. This is also a very effective solution. The charging power is adjustable according to the surplus energy. This looks like similar to this graph here. You see the car is now charged from 3 p.m. And following the production curve of the PV system. After 6, you see that the car will continuously be charged with a very low charging power of only 1.4 kilowatt. This can also be switched off or on. So this is just more or less to secure the charging as well when there was a cloudy day, that you will always charge with a kind of minimum charging power, which also can be set. In this case, we set it to 1.4 kilowatt. And with that, we have to make sure that the charging is done in the morning when the customer leaves his house. Yeah, then the last solution is for more commercial installations. You see we have here the Keva solution again with the Keva wallbox. So we use here 2 or more. The customer has got more EVs. Maybe it's a commercial building with 3 cars in this case. So we have more charging points. The charging points are linked to each other with load management. So that's what the master wallbox is doing already as a standard function. So that not all Keva wallboxes can do that, but the bit more professional one can do that. And then you have as well here an Ethernet connection to the inverter, and then the link in between is here in this case a Loxon mini server. This can be as well other devices which can do the load management. So whatever they just need to be able to read out the data from the inverter via Modbus TCP or SolarAPI, and then give this information, the right according information to the Keva wallbox. This can be as well SmartFox solution or this Loxon solution. Yes, that's here the example. What's very nice here with this solution, of course, is that you can have many wallboxes, and you just set the maximum charging power at the master. For example, you have 100 kilowatt available, and the control, the wallboxes will then share the energy on all wallboxes according to the needs of the customer. So here in this case, we can use a faster charging whenever we have PV energy, and if the PV is gone or in the evening, we'll reduce the charging power according to the maximum network limits, depending on of course, the location and the socket of the house, the connection of from the grid. Yeah, also RFID cards can be used here, and a charging app can also be used here. Now, let's see the economic potential. Basically, I have here just a private household example of Austria. We have a 5 kilowatt peak PV system. Basically, an average rough calculation. These households spend about 1,000 euro for fuel and 1,000 euro for the electricity. This is an annual cost, so 2,000 euros in total. Whenever we have a PV system, integrate a PV system, and we calculate and self-consumption, self-sufficiency of about 40%, we can achieve here savings of around 400 euros. So in total 1,600 euros are left. The rest is coming from the PV system. But now, if we integrate the EV charger as well, it looks very different. You see on the first one, when we have an EV which is controlled via load management from the PV system, from the Fronius PV inverter, we see that the costs for fuel are going down from 1,000 euro to only 300 euros per year. And of course, the other electric consumption will stay the same, remain the same, so will be no much different. But basically, savings are here at around 1,100 euro per year. And if we have a battery as well, let's say a 10 kilowatt hour battery, we have savings of more than 1,400 euros as an average here. So this is a basic assumption calculated with energy price, electricity price of 20 euro cents, and you see 5 kilowatt peak PV system. So that means the savings can be really very high when you integrate the EV charging into your PV system, and whenever you use the comparison to fuel, let's say diesel car to an EV. So that's a real big difference. And the conclusion, the savings, of course, are also depending on the daily mileage. So as more distance you go every day, as better, as high the savings. But of course, we also have to mention that with very high driving distances of more than 100, 200 kilometers a day, you will of course need as well a very big PV system. So make sure that that this is of course not very easy for everybody. Let's say in a commercial building, you usually have possibility for big PV systems. On a small residential house, you will of course be have some difficulties when this driver would like to go 200 kilometers a day. Yeah. Second, it's also about the user behavior. Is the vehicle charged during day, or if the customer only arrives at nighttime, then of course it's a bit more difficult. Third thing is, of course, as I said, the PV system size and the battery size. Bigger PV system, bigger battery is of course better. And the further factors are the load profile, what other consumption is in the building, and also the charging power, which I have selected. Usually lower charging power is better because that's also then good on for the cloudy days, and then you also have the benefit even of the cloudy days. And the further advantages, which are also very important, is you avoid peak loads and peak load tariffs. This is very important for commercial buildings who pay for that. And the possibility of higher charging power with PV integration. So you can, even with a small connection, network connection, I mean with a low fuse, you can charge your car with higher power whenever you use your PV power for the charging. So these are the additional advantages. Yeah, as I said it already, low charging rate gives higher self-consumption. Yes, finally, I would like to give you some further information. I also did in the documents, you can find another document about e-mobility solutions when you just go on the link here, on the document link, or you can also find that on our webpage. As well, you find trainings and webinars, more webinars and YouTube videos about e-mobility solutions of Fronius. And we will also send you, of course, the presentation tomorrow, and the recording you will also receive tomorrow of this presentation. Yes, that's it from me. And now I would like to ask Michael to give us some feedback about the questions from from our customers. Michael, did we receive any questions, or can we answer a few of them live here now?
Yes, of course. Thank you, Hans. And of course, we get a lot of questions from you guys during the webinar, and I want to answer some of them right now. So first question was about if Fronius will have their own charging solution in the future. And I can tell you, yeah, we are working on something here. And of course, you will get to know the latest information on that here in our webinars and on our Fronius webpage. So make sure, if you're interested in this topic, to check out our Fronius homepage and of course our newest webinars in the future to get more information on this topic. Furthermore, I want to give you a hint. You will get a recording and of course the presentation slides of this webinar. So if you hadn't got the whole webinar, or if you want to watch it again, you will get it automatically to your email address. We will stay online now for a few more minutes and answer all your questions. So if you have any questions left, please feel free to ask us them in the chat, and we will then try to answer them in the chat for you and also via email. So thank you very much for your attention today. All the best to you, and I say goodbye and to the next time here at Fronius. Goodbye.
Goodbye. Bye-bye.